Today we are going to see about CPU scheduling, basic concepts, the algorithms, and how multiple process scheduling is done and real-time scheduling is done by the CPU. So the basic concept of CPU scheduling is maximum CPU utilization obtained with multiprogramming. To make the CPU used in a better way, we are going to use the CPU scheduling algorithms to make the CPU work in a better way. Our motto is to make the CPU utilization maximum. And CPU IO burst cycle. Process execution consists of a cycle of CPU execution and IO wait. IO is nothing but input output. So a process will have definitely some inputs to be received and outputs to be displayed. So that for that IO process, it may wait for some time. And after that, CPU execution happens. After execution, it may wait for some IO input or output. So this is a continuous process. So this continuous process is called as a CPU IO burst cycle and CPU burst distribution. So how the CPU burst happens? So that is specified. Alternating sequence of CPU and IO bursts. So you can see in this diagrammatic representation, load store, add store, read from file. So all these are the commands to be executed by the CPU. So it is a CPU burst. Wait for IO. That means the process is waiting for some input or output device to be connected. So that is IO burst. And after that, again, it goes for store, increment, index, write to file, which are all commands needs to be executed by the CPU. So it is CPU burst. And then it will wait for the IO, and that is the IO burst. And again, it is executing some commands. So it is a CPU burst. So likewise, the CPU and IO bursts are executed in a cycle. So therefore, it is called a CPU IO burst cycle. What is a CPU scheduler? Scheduling the processes to the CPU, it's a big task. Which process needs to be scheduled to the CPU at a particular time? So for that, some algorithms are used. So those algorithms we are going to see consecutively. So this selects from among the process in memory that are ready to execute. So only ready process can be given to the CPU for execution and allocate the CPU to one of them. So more number of process may be waiting in the memory. So the CPU needs to choose a particular process and give it to the CPU, the memory CPU for execution. So for the CPU scheduling decision may take place when a process switches from running to waiting states. So when it happens is when a process is in running state and it is going to be in a waiting state, the CPU scheduling decision to be made. And from running state to ready state switching, CPU scheduler decision to be made. From waiting to ready, the CPU scheduler decision to be made. And when the process is going to terminate, the CPU scheduling decisions to be made. And you have two types of scheduling. One is non-preemptive, another one is preemptive. So scheduling under 1 and 4 is a non-preemptive and all other 2 and 3 is a preemptive scheduling. Dispatcher. So what is the work of a dispatcher in CPU scheduling is it gives the control of the CPU to the process selected by the short-term scheduler. This involves switching context, switching to user mode, jumping to the proper location in the user program to restart the program, and the dispatch latency. Time taken for the dispatcher to stop one process and to start another running is called as a dispatch latency. So the short-term scheduler will help you to take or select a process. So the work of the dispatcher is to give the control of the CPU to the process selected by the short-term scheduler. So when the scheduling started, the context switching happens, user mode switching will happen, and the pointer will be moved to a proper location for executing the program. Scheduling criteria: CPU utilization, throughput, turnaround time, waiting time, and response time. So all these things are considered before scheduling any process to the CPU. Keep the CPU as busy as possible. That means the CPU should not be idle at any point of time. Throughput: number of processes that completed their execution per time unit is called as a throughput. If a CPU is possible to execute 5 processes at the given time, then it is the throughput value of the CPU. What is the turnaround time? Amount of time to execute a particular process. The execution starting from the first line execution to the end line execution, the time taken is called as a turnaround time. Waiting time. So the amount of time a process is waiting in the ready queue before it starts the execution, or due to some reasons, IO waiting or the sub-process scheduling waiting, the process will be in the ready queue. So those time will be called as a waiting time. And response time: amount of time it takes when a request was submitted until the first response is produced. That is called as a response time. So the process has been given to the CPU, and the CPU, the time taken by the CPU to start the execution of the process, the difference between that time is called as a response time. Optimization criteria. So the maximum CPU utilization to be made. So that should be maximum. So throughput should also be maximum, and the turnaround time should be minimum. So what is the turnaround time is amount of time to execute a particular process if it is a maximum turnaround time. So every process will take more number of time. So therefore, the CPU can be utilized in a very less way. So that should be only minimum. Waiting time should be minimum. So we all know that even when we travel, we don't like to wait for a long time. So likewise, the waiting time of a process to get executed should not be a maximum one. Therefore, it is a minimum one. And the response time is the starting time of the process for execution is called as a response time. If it takes much time, maximum time for the response, then every process will be executing for a longer period of time. So therefore, it should be in a minimum state only. Only the CPU utilization should be maximum and the throughput should be maximum. So what is a throughput is a completion of a process in its execution is a throughput. So if more number of process gets completed, then the CPU is utilized in a better way. We can say that. So therefore, the throughput should be in a maximum optimization criteria. First come, first served scheduling. So what is first come, first served? FCFS scheduling is you have given 3 process P1, P2, P3 and burst time of 24, 3 and 3. So the concept of FCFS scheduling is whichever process comes first, that will be scheduled first in the CPU. That will be scheduled for the CPU to execute. So a Gantt chart is a chart which provides the details about how the process are allocated to the CPU based on the first come first served basis. If you take this Gantt chart as an example, in 0th time, the P1 process arrived and it is the burst time of the P1 process is 24. So at the time of 24, the P1 process stops its execution. It completes its execution. And the P2 arrives next. So when the P2 arrives, the burst time of P2 is 3. So from 24, if you add 3, that is 27 is the stopping time of P2 process P2 execution. And you add 3 more burst time for the P3 to be executed. So 27 plus 3 is 30. So the stopping time of process P3 is 30. So the process P1 executed till 24 milliseconds, and the process P2 executes till 27 milliseconds from 24 milliseconds, and P3 starts its execution by 27 milliseconds and ends it by 30 milliseconds. So what is the waiting time for each and every process we have to calculate? So the waiting time of P1, so it starts from 0th milliseconds. That means it doesn't wait for any, um, it doesn't wait for its execution. So therefore the waiting time for P1 is 0. What is the waiting time of P2 is? The P2 can be executed only after P1 gets completed because it is the first uh, process which came. So therefore, P1 gets executed only at the 24th, completed its execution only at the 24th millisecond. So therefore, P2 needs to wait until P1 gets executed. That is, it can start its execution only by 24. So it waited for 24 milliseconds. So P2 equal to 24. That is the waiting time. And P3, it waits till P1 and P2 gets completed. P2 gets completed only at the time of 27 milliseconds. So the waiting time of P3 is 27. So you have to find the average waiting time. So it shows that 17 milliseconds is the execution time of this 3 process, which is having the burst time of 24, 3 and 3. And it also follows the scheduling type of FCFS. So it is a 17 millisecond. When you compare it with other scheduling algorithms for the same process and same burst time, whichever algorithm gives you the lowest average waiting time can be taken for uh, assigning the process to the CPU. So according to this FCFS, it is 17 milliseconds for the 3 process. Suppose that the same process arrive in some other order. Instead of arriving at as P1, P2 and P3, it is arriving in P2, P3, P1. So according to FCFS, whichever process comes first will be allocated. So P2 is allocated first. So it starts in 0th milliseconds. It is the burst time of P2 is only 3. Therefore, it ends in 3 milliseconds. And similarly, after that P3 came. So P3 starts in 3rd milliseconds and the burst time of P3 is 3. So therefore, in 6th millisecond, it gets stopped. And the burst time of P1 is 24. It comes after P3. So therefore, it starts its execution by 6th millisecond and ends it with 6 plus 24, 30th millisecond. So if you find the average waiting time of these process, P2 waited 0 and P3 waited for 3 and P1 waited for 6 milliseconds. So 6 plus 0 plus 3 divided by 3 is going to be 3. So that means if the process arrives in this order, the average waiting time is only 3 instead of 17. So if the process arrives in order of P1, P2, P3, it is taking much average time, average waiting time. So the convoy effect is nothing but a short process behind long process. That means P2, P3 is having only short burst time. P1 is having longer burst time. So we have to take the shorter burst time to be executed first and complete all the shorter process. And then we can take some time for executing the longer process. So this type of execution is called as a convoy effect. So the next type of scheduling is shortest job first scheduling. So in this scheduling, whichever process has the shortest milliseconds or shortest burst time will be taken for execution. So associate with each process the length of its next CPU burst. Use these lengths to schedule the process with the shortest time. So it could be a preemptive or a non-preemptive type of shortest job first scheduling. If it is a non-preemptive type, one CPU given to the process, it cannot be preempted until completes its CPU burst. Until all the execution gets stopped, the CPU cannot relieve that process from execution, that is non-preemptive. So the process which came after the process in execution to is needs to wait until the process being executed gets completed. And what is preemptive scheduling is if a new process arrives, so automatically CPU checks for the shortest time. If it is a shortest time, it will preempt the process which is already in execution and gives the current process into the CPU execution. So, um, so this could be called as the shortest remaining time first scheduling. So SGFS is optimal. It gives the minimum average waiting time for a given set of process. So example of this non-preemptive SGFS process P1, P2, P3, P4. The arrival time of each process is given and the burst time is given. When you place the Gantt chart according to non-preemptive method, non-preemptive is see the process needs to wait until the process in execution gets completed. So therefore, P1 arrive at the time of 0. So P1 is started for execution. The burst time is 7, and before it reaches the burst time, P2 arrives at the time of 2 milliseconds. So at the time of 2 milliseconds, even though it arrives at the second millisecond, even though it has the shortest job first, it is not preempted. So it has to complete its execution, then only P2 will be allocated. So after getting completed at the 7th milliseconds, P2 needs to be allocated. But at the time of 4, P3 comes first. P3 arrives, process P3 arrives, and the arrival time is 4.0. So when P1 is getting executed, two processes has arrived, P2 and also P3. But anyway, when you compare the shortest burst time, one is having in P3. So therefore, the P3 will be allocated at the time of P1 gets executed, P1 gets completed its execution. So after 7th millisecond, P3 is allocated. The burst time is 1, so it gets completed at by 8th millisecond itself. So now P3 is completed, P1 is completed. And after that, at the time of 5, that means P3 is in execution state at the time of 5th millisecond, P4 arrives. So even though P4 arrives, when you compare the P3 value and the P2 value and the P4 value, it is going to be only the same. That is 4 and 4. So therefore, anything can be allocated after the P3 gets executed. So therefore, P2 is allocated first and then P4 is allocated. So totally it takes the time of 16. So when you find the average waiting time of P3, P1 is 0 and P3 is 6. So what is the reason for the 6s? It arrives at the time of 2. So therefore 7 minus 2 is 4. 7 minus 2 is 4. And the waiting time needs to be lessened. So 7 minus 2 minus 2. So totally it is going to be 6. So you can see here in P2 is started at the time of 8. So therefore 8 minus the arrival time 2. When you subtract the arrival time with the starting time, you can find that the average waiting time of P2 was 8 minus 2, 6. So that is what given here. And when you go for P3, it comes at it arrives at the time of 4, but the starting by 7. So 7 minus 4 is 3. So that is the average waiting time of P3. And P4, it arrives at 50 millisecond, but it starts its execution by 12th millisecond. So 12 minus 5, 7. So when you find the average waiting time, it is 4 milliseconds. That means the process and execution will not be stopped even though a new process arises with shortest burst time. And this is the example of preemptive SJF. So process P1, P2, P3, P4, the arrival time is 0240 and the burst time is 7414. As this is a preemptive method, when a process arrives, when a process is in execution, another process arrives, we have to check the burst time of each process, two process, whichever is slow or whichever is low, that value, that process needs to be executed. So therefore, the process is in execution will be preempted. So therefore, here process P1 arrives at 0th time. So P1 starts its execution, but at the time of 2, P2 arrives. When you compare the burst time of P1 and P2, P2 was 4 only, so which is lesser than 7. So therefore, stop the execution of P1 at the time of 2 milliseconds, and P2 starts its execution. So totally, it has 4 burst time. But when it was executing at the second burst time, that is at the 4th millisecond, P3 arrives. So again, we have to compare the P2 burst time and the P3 burst time. So you can see that P3 is having a lesser burst time value, that is 1. So therefore, P2 is preempted and P3 is inserted. So at the time of 4th millisecond and within 1 millisecond, that is 5th millisecond, P3 gets completed. So after that, at the 5th millisecond, P4 comes. The burst time of P4 is 4, and the waiting and the half executed process P1 and P2 is having lowest burst time. So when you compare to P1 and P2, P4 is having the lowest burst time. Sorry, P2 is having the lowest burst time. So therefore, P2 starts its execution. So at the 5th milliseconds, and P2 gets already two burst time is over. So the remaining burst time out of 4 is for P2 is 2. So therefore, it starts by 5 and ends by 7. So once P2 gets executed, so checking for the burst time of P1 and P4, P1 has 5 and P4 is 4. So P4 is the smallest burst time. So therefore, P4 will be start executing. So 7 to 11, P4 gets stopped. And after that, 11 to 16, the remaining 5 milliseconds, P1 finishes its execution by 16th millisecond. So when you find the average waiting time of P1, you can say that it has been waited only 0 milliseconds. But actually, it is 11. In the 11th millisecond, it again started its execution. And in the first time, it finishes its execution by 2 milliseconds. So 11 minus 2 is 9. So that is the average waiting time of P1. So P1 finishes its execution by 2nd millisecond, and it waited until it gets the last schedule, that is at the 11th millisecond. So already 2 milliseconds it has executed. So therefore, we are subtracting 11 minus 2 for the P1. And what is P2? When you check for the average waiting time of P2, it's 4. It completes its execution, but it starts its execution for the second time is 5. So therefore, 5 minus 4 is going to be 1. And what is P3? P3, it came by 4th millisecond, but it started its execution at the 4th millisecond itself. Therefore, P3 doesn't wait it, so it's 0. And when you go for P4, P4 is at the 7th millisecond, at the 5th milliseconds it came, but it starts its execution by 7th milliseconds only. So 7 minus 5 is going to be 2. So when you divide it by 4 and find the average waiting time, it is going to be 3. That is the preemptive SJF waiting time. So when you compare preemptive or non-preemptive is having 4 milliseconds of average waiting time for the same set of process, but preemptive is having only 3 milliseconds of average waiting time. So therefore, which one is better? So preemptive SJF is better than non-preemptive. And priority scheduling. What is the next type of scheduling is priority scheduling. A priority number is associated with each process. Whichever has the highest priority, that will be executed first, and then lowest priority needs to be waited until highest priority process gets executed. The CPU is allocated the highest priority and the smallest integer value. What is the highest priority is the smallest integer value. That is 1 is the highest priority because it is the smallest integer value. So it could also be based on preemptive or non-preemptive. And SGF is a priority scheduling where priority is the predicted next CPU burst time. So we are preempting the process from the SJF based on the priority what we are giving for the burst time, smallest burst time process which arrives next. So therefore SJF is a priority scheduling. And the problem what actually happens in priority scheduling is starvation. That means all the highest priority process will be executed continuously. The lowest priority process will be starving for more number of time. So therefore, we are going to add some aging concept for the starvation. That means you are going to add or increase the priority for the lowest priority process after all the highest or some of the highest priority process gets executed. So that is a solution which is called as aging. That means increasing the priority of the process so that it becomes the lowest priority process becomes the highest priority process, and it will be executed. And the next scheduling is a round robin scheduling. So it's like a round table uh, round table conference. So from zeroth process, P1 process to PN process, after executing PN process, again P1 process gets executed. So that is the round robin scheduling. And each process gets a small amount of CPU time, that is time quantum will be assigned in round robin scheduling, usually 10 to 100 milliseconds. After this time has elapsed, the process is preempted and added to the end of the ready queue. So if there are n processes in the ready queue and the time quantum is q, then each process gets 1 by n of the CPU time in chunks of at most q time units at once. No process waits more than n minus 1 q time units. The performance is, when the queue is large, it has to use the FIFO technique. When a queue is small, we have to use only the must be large with respect to context switch. Otherwise, overhead is too high. So we have to use the round robin scheduling only. So example of round robin with the time quantum 20. So P1 process is having a burst time of 53. At the 0th millisecond, P1 gets started, but only time quantum is 20. So only 20 milliseconds will be executed by P1. And after 20, P2 gets executed. Next process, it stops by 17 milliseconds itself. So at the time of 37, P2 gets executed. But after that, P3 arrives, it is having 68. So even though it has 68, 2020 time quantum will be allocated. So it needs to wait until the next ready queue gets started. So therefore, P3 gets stopped by at the time of 57, and P4 is arrived. So P4 is 24. So from 57 to 20, it is going to be 77, but the uh, uh, four burst time needs to wait. For burst time is still available for P4, but the P4 needs to wait until the round robin is scheduled. So after P4 gets executed, we'll check whether whichever process is having some more burst time to be executed. So P1 is the next ready queue process. So P1 will be taken. Already 20 milliseconds is executed, but still it has 33 milliseconds. So again 20 milliseconds will be executed. So 13 milliseconds, the P1 needs to wait again in the round robin. So after that, P2 is actually completed already, so no need for the second chance. So it goes for the P3, already 20 milliseconds is executed. So therefore it's 48. So again 20 milliseconds of P3 gets executed. After that, P4. So it goes on until all the process gets executed, but only the time quantum is given as 20. So if the time quantum increases, so more number of process will be in a waiting state. So therefore, you have to assign a lowest time quantum for better performance. Multi-level queue scheduling. Ready queue is partitioned into separate queues. That is foreground queues and background queues. Foreground queues will have interactive programs and background queues will have batch programs. Each queue has its own scheduling algorithm. Foreground will uses the round robin scheduling and background will uses the first come first serve scheduling. So scheduling must be done between the queues. It could be fixed priority scheduling, that is serve all from foreground, then from background. So as the background process is still waiting, there is some possibility of starvation for the background process. Time slice, each queue gets a certain amount of CPU time as like a round robin. So 80% to foreground and then 20% to background. But the background process uses the first come first served scheduling process, scheduling type, scheduling algorithm type. So therefore, whichever process comes first in the background, that will be allocated for the time quantum given in the RR. So this is the diagrammatic representation of multi-level queue scheduling. Highest priority process were there, and also the lowest priority process. So the based on the RR or FCFS, all the process gets executed. Multi-level feedback queue scheduling is nothing but moving the process between the queues in order to make the aging gets completed. So multi-level feedback queue scheduler defined by the following parameters. Number of queues. If the number of queues gets increased, so automatically aging needs to be increased. Scheduling algorithms for each queue. Each queue can have different scheduling algorithms. Method used to determine when to upgrade a process. So there is a method when to give the highest priority for the process, when to demote a process, when to make the process lesser for the process to become a lower priority process. And the method used to determine which queue a process will enter when that process needs service. Because so much of queues we are going to follow. So the time quantum for the queues will be given either 8 or 16, and the background process will be using the FCFS scheduling in the same way. And the multiple process scheduling is CPU scheduling more complex when multiple CPUs are available. So if more than one CPU is available, scheduling becomes a tedious process. If it is one CPU itself, this scheduling is a tedious process. When more than one CPU is connected for process, it becomes a tedious. So therefore, homogeneous process within a multiprocessor can be used. Load sharing can be done, and asymmetric multiprocessing technique will be used. That is, only one processor accesses the system data structures, alleviating the need for data sharing. So one processor will be dedicatedly used for accessing the data structures, and the data sharing is done by that particular processor. So that type of processing is called as the asymmetric multiprocessing. Symmetric multiprocessing is nothing but at the same time more than one process starts its execution with getting the data structures and data sharing, then it is a asymmetric multiprocessing. What is a real-time scheduling is? Two types of real-time scheduling is available. One is hard real-time and the soft real-time. Hard real-time needs a critical task to be executed within a stipulated amount of time. And soft real-time is nothing but critical process receives priority. So based on the priority, it is executed. And what is dispatch latency is event response to event. So the response interval is nothing but the event gets starting time is very low. So it is a response interval, and this interval may be called as a dispatch latency. And some interrupt happened. After the interrupt gets cleared, process made available, and the real-time process execution also happened. So the starting of the process and the time waited for the real-time process execution gets started is called as a dispatch latency. So there may be a conflict which makes the dispatch latency. That means waiting time was there. If any conflicts happens, the process stops it. The CPU stops the processor execution. After the conflicts get cleared, again the processor wait until it reaches the real-time process execution. So therefore, the conflicts and clearing of the conflicts and dispatching to the process to the real-time process execution for, and then which responds to the event, that time is called as the dispatch latency time. Thank you, students.